Okay, yeah, it's our pleasure to sponsor the HPC Forum. Uh, many of the people here, HPC User Forum, many of the people here know Reservoir Labs for its innovation and technology and good work in compilers. For 30 years, we've been working on very advanced architectures, and now there's so much architecture innovation, new processors, new domain-specific processors, and our compiler team is helping people get their applications ported faster to those processors, increasing the uptake of new AI models and achieving great performance for those complicated architectures. We're also working on very advanced algorithms and asymptotic speedups on things like inverting Maxwell's equations um, in linear time. So for folks who are interested in that, they can check out our website. So today, um, talking about, I would just want to introduce another thing that we're working on at Reservoir called the gradient graph, or G squared, or G2. And this is a tool for getting more data through networks and many other things. So before I get into it, I just want to thank the team, Jordy, Sruthi, Noah, Brendan, Jamie, Lucy, Jim, Allison, for the great work on this. And also thank our sponsors. We have sponsorship from the Navy and also the Department of Energy Office of Science, Advanced Scientific Computing Research, Barb Helen's program, and the great program managers there, Rich Carlson. So yeah, let's get into it. So, oops, right hand button. Okay, so for high performance computing, we see this incredible demand getting created to move data around global networks. So there are research and education networks. There are also commercial networks. This is a picture of Google's B4 WAN that was published in 2017. For research and education networks, there are scientific collaborations, streaming sorts of computing, the kinds of distributed and federated applications happening at the regional, national, global scale. And data is getting produced by scientific experiments at incredible rates. And this has to get moved around storage and processing and other collaborations. That's coming from the LHC, genomics, astronomy, physics. And that's also happening in the commercial sector. The movement of logs for cybersecurity or transaction data at banks, training data for AI models, and the movement of the models themselves. And there's about to be an incredible increase in demand on the networks coming from 5G, new applications, telemetrics, AI on demand, moving models to the edge, and various forms of augmented and virtual reality. So people know about the congestion control algorithms that are typically used to control and kind of manage the data moving around these networks, Van Jacobson's algorithms, TCP slow start, but that is not enough. Those algorithms are running out of steam. And the reason is that bottlenecks form structures. So a single bottleneck is kind of a symptom, but there's a whole set of dynamics in a network related to the interaction of networks, interaction of bottlenecks as they form and reform as demand changes and as the network changes. So with this great sponsorship from Asker, we've built a theory related to the formation and dynamics of these bottlenecks. And our papers are on our website. There's a stylized notation to indicate the links that connect the nodes, the flows that create demand on that, and then the G2 algorithm is able to create, on the right-hand side, a kind of dependence graph among the flows and the links in the network. And it's a DAG, and that allows us to calculate the effects, because it's not just the bottleneck structure statically, there's a kind of gradient that we can compute, and that allows us to do things like if there's a perturbation on a link, what happens to the various flows that not just cross that link, but then the links that the affected flows also cross, and then downstream other flows. And that's the bottleneck structure and the effects of changes and the use of this gradient. We can look at the effects of changes in demands on a flow. F4 is a flow, and look at how that affects the performance of other flows. And we can do that very quickly and in a localized fashion because we have this bottleneck structure computed from the logs. So the way the system works, we take topology info in on the left along with flow logs. We run our algorithms, and there are various ways to interface to that, user interfaces and also a programmable REST API. So what is this good for? Classically figuring out what are the elephant flows, and the bottleneck structure actually lets you find out which flows really control the overall throughput of the network, and it's not necessarily what you'd call the heavy hitter flow. So for more information on that, check our papers out. We can do dynamic routing. We can figure out for flows where they should be routed. And doing that, you can see here, we can get a 74 or 75% increase in the flow rate by using this theory. Many data centers are constructed with a fat tree topology. There are ways to use the theory of bottleneck structures to do capacity planning. This application where we have time-bound constrained flows, we have to get across the network. The theory of bottleneck structures will help figure out the best way to get those flows through the network. And that's directly applicable to some of these science applications where I have to move large volumes of experimental data around the research network. In supercomputer networks, there are all sorts of interesting topologies, Dragonfly, and so forth. Theory makes predictions about how to design those. We can also use it for more business-oriented applications like making sure the service level agreements are met by a network. And here's an example just done in terms of the Google B4 network. So what are the innovations here? That we can compute this bottleneck structure in real time. Some very fast algorithms actually kind of related to backpropagation in a neural network to very quickly compute the gradients in this bottleneck structure to allow us to predict the effects of changes. We have a dashboard, a user interface for people to experiment with changes and understand what's going on, both statically in terms of looking at logs and also dynamically in terms of what's going on in the network now. You can see some of the diagrams here where we're identifying critical flows to the performance of the network. Ways to use this user interface to find better paths for data. So if you're managing large volumes of data through a science network, this should be a good tool. Looking at the what we can do in terms of making changes to increase the overall system throughput. And in general, this is good for the entire network life cycle from the planning to the capacity, network design, capacity planning, to the operation of the network. And this is good for both physical and virtual networks. So if you're interested, go to our website. We have our various papers. Also, we'll be at Supercomputing in SciNet in a collaboration with several of the research networks out there, GNAG, Caltech, PRP, ESNet, and with our collaborators at Columbia and Yale. So those experiments are being designed right now. Okay, and here's the current status of GradientGraph. We've got initial deployments going on with various research and educational networks, along with the DOE's ESNet. We're looking forward to additional collaborations to test the technology, particularly in data center and supercomputer fabrics. So if you have a data center or a supercomputer, please get in touch. We'd love to work with you. And when you're at SC21, Supercomputing Conference in November. Stop by SciNet to talk with the team. And for more information on the gradient graph technology, it's www.reservoir.com/gradientgraph. And you'll find links to our papers on the website, along with various examples on the technology. So thank you very much, and have a great forum.